Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about translations and glide reflections. So let's get started with the following do now. For the first problem, it states that we have a triangle ABC undergoing a combination of transformations. Namely, first, we're reflecting the triangle over the x-axis, then we reflect that image over the origin, and then we reflect that new image over the x equal to 5 line. And we're given the 3 points A, B, and C. And secondly, how can the composite transformation in problem 1 be described as one type of transformation? So let's look at this. Okay, so here we have the original points and the triangle drawn in a coordinate grid with the x and y axis. Now, the first transformation was a reflection over the x-axis. As you remember from the previous YouTube video, when we reflect an image over the x-axis, we are negating just the y values. And there you go is our new image. A prime, B prime, and C prime with the same x coordinates but negated y coordinates. The next was a reflection over the origin. So when we reflect over the origin, we learned that you're negating both the x and y coordinates to obtain the following image. So now the image is located in the first quadrant as A double prime, B double prime, and C double prime. And finally, we're reflecting the triangle over the x equal to 5 line. Notice that that line is a vertical line at x equal to 5. So reflecting it over, and we end up with A triple prime, B triple prime, and C triple prime. And I know it sounds funny, but that's how you would pronounce it. Okay, so now if you compare triangle ABC and triangle A triple prime, B triple prime, and C triple prime, how could we describe that as in one single transformation? Well, you can view it as a translation going from this triangle over to this triangle here, okay? And that's basically the introduction to translations. So let's define translations. What is a translation? A translation is a transformation in which each point in a figure slides a certain distance and in the same direction. So here's the example. We have the triangle, but then you translate in the same direction this way. As in, you can see here, each vertex gets mapped into a straight path here. Now, when you move all the points in a straight path, as shown in the figure here, that is also referred as a rigid motion. So let me define rigid motion for you. So a rigid motion is any way of moving all the points in the plane such that A, the distance between points stays the same, and B, the position of the points stays the same as well. Now, as you go back in the figure here, we know that all these distances here are the same. They're all congruent. So that satisfies part A. And also, we know that the triangle stays in the same orientation, which is also part B of the definition of rigid motion. Now, what are all the types of rigid motion? And as a matter of fact, there are 4 types of them. So let's think about this. Is a reflection a rigid motion? Are the distances between the points the same? And is the position of the points the same as well for reflection? Well, we know that that is true for translation, but what about reflections? What about some other transformations? Well, it turns out that these are all the 4 types of rigid motions, okay? Again, rigid motion, you can think of it as the object not becoming bigger or smaller or distorting, but it actually stays congruent to the original object. So that's really the key of understanding rigid motion, that the object will remain congruent and every point will be translated or moved or transformed at a specific distance. Okay, so reflections is one of them. Translations is also a rigid motion. And We are going to learn in today's YouTube video also about glide reflections. That's also part of a rigid motion. And in tomorrow's YouTube video, we will learn about rotations and why that's a rigid motion. So I also put a website here. You feel free to check it out. So basically on this website of rigid motion, explains what it is and what the rigid motions are, translations, rotations, reflections, and glide reflection. And it explains exactly why it's a rigid motion and so on. So, feel free to click on the website that is posted on this YouTube video in the comment section. So here's the notation for translation. For translations, you use capital T, and then you put a point x comma y, and as a subscript, you put a comma b, okay? So a comma b are linear distances in the x and y direction respectively, for which you move the point. For example, if you translate a point xy by an amount of a comma b, you must add a to x and b to y, as shown in the figure here that follows. So here you have the xy coordinate axis, a point xy. So you translate the point by an amount of a in the x direction and by an amount of b in the y direction. So you must add the a and b value to x and y respectively. So that is basically the notation for translations. So here's an exercise for you. If you want, you can pause the video here. Write the transformation notation from the do now for each point, okay? So if you go back to the original problem that we had, for example, we're going from point A here, right, to point A triple prime, and that's the translation from A to A triple prime. What do you notice here? That we're translating it to the right by 10 units each time, right? But the y stays the same. So how would you write that in translation notation? So for the first point A, you would write the following: that you're translating negative 10 comma 4 by an amount of 10 comma 0 to obtain the point 0 comma 4. And now you can do the same thing for B and for point C, okay? So that's how you write the do now translation in this example. So this is how you write the transformation notations from the do now. So let's look at an example here now. For part 1 of that example, find the image of h negative 1 comma 3 under the translation t sub 2 comma negative 1. Okay, so you would write it like this, t, and then we write the 2 here, comma negative 1 of point negative 1 comma 3. Okay, so what do we do here? We just simply add. So we do negative 1, we add 2, comma, and we have 3, and we add negative 1 in this case, okay? So the answer should be here, if you do the math, 1, comma, 2. And that is the image under the translation t2, comma, negative 1 of point h, okay? Now for part 2, if a translation t maps point negative 3 comma 1 onto p prime of 5 comma 5, what is the translation t then? So basically we're looking for the a comma b value, right? So here first we have negative 3 comma 1, and that is equal to 5 comma 5. So basically you can just simply write an equation and say that this is going to be equal to, well, we're going to have negative 3 plus a, comma, and here we have 1 plus b, okay? So now we know that this has to be equal to 5, and this also equals to 5, okay? So negative 3 plus what is equal to 5, okay? And the answer here is a is equal to 8, okay? And for here, for b, we have 1 plus what is equal to 5, so the answer must be 4, okay? So the answer here is just simply 8 and 4, okay? Now for part 3, it says here that now we want to find a composition of transformations, okay? So let's do that. First, let's translate the point 1 comma 3 by an amount of 2 comma 0, okay? So here we end up with 3, comma 3. And then after that, we take the point 3, comma 3 and reflect that over the x-axis. Okay, so let's do that. So again, when you reflect a point over the x-axis, you negate the y value. So you end up with 3, comma, negative 3, and that is the answer, okay? So let's sketch that scenario. So as you can see here in the figure, we start at point 1, comma 3, then we translate by an amount of 2, comma 0 to get 3, comma 3, as we calculated previously, and then you reflect over the x-axis to end up at 3, comma negative 3. Now, this type of transformation is called a glide reflection because this part is defined as the gliding part, and then when you reflect over the x-axis, that is defined as the reflecting part. So that's why that is called a glide reflection. It's basically a reflection followed by, or a translation followed by a reflection, okay? And you can actually keep doing this over and over again. So let me first define the word glide reflection. So here's the definition. A glide reflection is a composite transformation which is translation followed by a reflection in line parallel to the direction of translation. Now, why do we even have glide reflections? Because it turns out that there are a lot of real-life applications that can be modeled using glide reflections. And here's an example. Footsteps in the sand. Well, why can you say that that is a glide reflection? Because it's simple, right? Because here, for example, you start at that point, you glide here, and then you reflect over, okay? And similarly, then you continue glide and then reflect. Glide, reflect, and so on ad infinitum. So that is the model for glide reflection, okay? Now, it turns out that there are 3 theorems that are true with translations. And it turns out that these theorems are actually true for other transformations as well. For example, the first one is under a translation, angle measure is preserved. Or secondly, under a translation, collinearity is preserved. And under translation, midpoint is preserved. So how would you prove these theorems? So let's take the first theorem. Under a translation, angle measure is preserved. So you'll prove it the following, okay? And it's actually also written here. Now let's say you draw the x and y coordinate here. And let's say you have some triangle ABC like that, okay? A, B, C. And notice this is actually a general case. Now here we have A prime, B prime, and C prime, okay? So here you're translating the entire triangle. Now look what it says here. Now you're considering A prime, B prime, C prime, that triangle to be the image of triangle ABC under the translation AB, okay? And by the way, the translation can also be in some other direction as well, okay? For example, you know, let me put that in a different, let me put it down here like that, okay? Or maybe here, there you go. Something arbitrary. So now in this case, we have a translation that occurs from here to here like that by an amount of A comma B. Okay, so that's the translation. Now what it says here is that, okay, distance is preserved, okay? So that's something that you need to know that is actually a postulate that is always true for translations, for reflections, for rotations, and also for glide reflections, okay? So if you know that this is preserved, as a matter of fact, we know that because it's a rigid motion, then what must be true is that in this case, for example, if you read this, that A is equal to A prime, B prime, okay? So we know that these two segments are congruent. Now, also, we know that BC equal to B prime, C prime. Okay, so we know that these two are congruent. And we know that these two segments are congruent as well. Okay. Now, what happens when you have two triangles in which all segments are congruent because of distance is preserved? Well, what happens here that then these two triangles must be congruent by the Sss postulate. Okay. Now, since the two triangles are congruent, then by corresponding parts of congruent triangles are congruent, then the angles must be congruent as well. Okay, so this angle is congruent to this angle, angle C is congruent to angle C prime, and angle B must be congruent to angle B prime as well. So that's basically how you would prove the first theorem, okay? Now, for the second theorem, under a translation, collinearity is preserved, how you would prove this one. Again, imagine you draw the x and y axis, okay? And let's say you draw a line here. Let's call it segment ADB. Okay, so we have segment ADB here. And let's say you translate this segment somewhere else. Let's say you translate it here, such that you have A prime, D prime, and C prime. Okay, actually there should be a B prime over here. We don't have any C here. So now it says here that, okay, since AD and C are collinear, we know that this has to be true, okay? So you know that AD plus DB equals to AB. And we know, again, the postulate that distance is preserved. Again, it is preserved because it's a rigid motion, okay? So therefore, we know that in this case, we know that, you know, if you look at segment AD, that has to be congruent to segment A prime, D prime. And similarly, segment DB has to be congruent to segment D prime, B prime. And what else? That we have segment AB has to be congruent to segment A prime, B prime. Okay, so everything is preserved here. Now, you can also look at the following here. By substitution, you know that this has to be true, okay? That's basically the segment addition postulate that you're saying, okay, segment AD prime plus segment D prime B prime is equal to segment A prime B prime. Now, if this was not on segment A prime B prime, then what will happen in this case? Then we will have the following scenario, okay? So just imagine if, let's say, D prime was here, okay? Then you end up with a triangle. And in which case, then you have A prime, D prime, plus, then you have D prime, B prime. If you add those two segments, that will be greater than segment A prime, B prime, okay? But the thing is that because it's a straight line, right? Because a straight line is the shortest distance between 2 points, we know that this has to be true. Therefore, the points must be collinear, okay? So again, the key here is that distance really is preserved, and you go from there. Now, the third theorem, and the translation midpoint is preserved, that is actually very similar to what we did previously, okay? So if you, again, have the x and y axis here, and let's say you draw a segment, so let me call this A. Now, M is the midpoint, and we have point B here, okay? So these two are congruent. Okay, so we want to prove that if you translate it here onto A prime, M prime, B prime, we want to prove that M is also the midpoint of A prime, B prime, okay? So again, this is simply by saying distance is preserved, we can actually prove it, okay? So if we say distance is preserved, then we know that A prime, M prime, that the segment is equal to or congruent to segment AM prime, okay? We also know that segment M prime, B prime, that is also congruent to segment MB, okay? And all of that because of distance is preserved, okay? So basically, so that's basically it, okay? So that actually proves it, okay? There's really nothing much to say here, but anyways, that's the proof for the theorem that the midpoint is preserved, okay? So that's basically it for today's lesson. You know, we learn about, again, translations and glide reflections. We learn what the notation is, and also we learned the important 3 theorems that you must know here. Okay, so I hope you enjoyed this lesson. If you enjoyed it, please click like. Also, don't forget to subscribe. Thank you for watching and have a great day.